Adelante.
Hi, everybody. Welcome to our second day of this EXCEED webinar in nature-based solution in coastal ecosystems. So first of all, I want to apologize for yesterday's inconveniences. We had some technical difficulties and we couldn't restore the connection. So we already have we record the presentations that you missed from yesterday, and you will find the link for YouTube video with all the presentations in the description of this video, so if you can watch them later. So we will start today with the presentation of our colleague Saber El Sayed. He works at the Technical University of Braunschweig. So, well, I will leave him the floor. So, thank you, Saber.
Hello, Valeria. Thanks for introducing me. Hello, everybody. Today I'm going to speak about improving soil properties of natural coastal barriers as a natural-based solution to mitigate coastal erosion and flooding during storm surges. So the main topic of today is natural coastal barriers like dunes and the barrier islands. And so this work is done in the Technical University of Braunschweig in Germany, Lich's Vice Institute for Wasserbau, and I'd like to thank the colleagues in Mexico for inviting me to give this presentation today. So I'm going to talk about the significance of natural coastal barriers. Then I'll speak about erosion of natural coastal barriers, the driving processes, and also a role of soil properties in mitigating coastal erosion.
Sorry, Saber, for interrupting. You are not sharing your screen. If you want to share your presentation.
Okay. Is it shared now?
We can see the Teams window, not your presentation.
Now?
No, I think you should select the PowerPoint window.
Sorry. Now?
Yeah, we can see it now. If you select the presentation mode.
Okay. So,
great.
So the topic is improving soil properties of natural coastal barriers as a natural-based solution to mitigate coastal erosion and flooding during storm surges. And as said, this work is done in the Technical University of Braunschweig in Germany and the Lich's Vice Institute for Wasserbau. I'd like to speak about the significance of natural coastal barriers, the erosion of natural coastal barriers, the driving processes, and the role of soil properties in mitigating coastal erosion, how to improve soil properties to enhance resilience of coastal barriers against erosion. And then I'm going to talk about the extension of the XPeach model to account for spatially varying soil properties. This will come later. And then I'll present at the end of the presentation a case study of natural coastal barrier of varying soil properties. I will end my presentation with a summary and conclusions about this topic. So here are two maps. One from Germany at the right side, and the second is sorry. So. Here we have this map here is for the north of Europe. Here we have Germany and the Netherlands, and we find that we have here many barrier islands that actually protect the north of Europe from storm surges and flooding. Actually, this kind of barrier islands, they reduce power energy, they attenuate power energy, and also protect the beaches here in the north of Germany from effect of storm surges and flooding. If we go to the Gulf of Mexico, and here we find the United States and Mexico, we will find that we have also here many barrier islands that protect the east of Mexico from flooding during storm surges. So if we look at how many barrier islands we have all over the world, we will find that we have almost 15% of the world coastal lines. They are formed by coastal barriers and dunes, and then we will find that natural coastal barriers are there are many forms, landforms, like we have barrier islands that actually uh, uh, protect here this lagoon, and we have Timblo and dunes. So this kind of landforms are very attractive for tourism purposes, and as said, they attenuate wave power before reaching the beach, and also work as a first defense line against surge and protect coastal areas from coastal flooding. So they are very important elements that actually for flood protection. Uh, uh, yeah, uh, the problem that actually these barriers like dunes or barrier islands here, they may breach during storm surges. Then we have catastrophic floods and very high inflow velocities, and then we have flood in our hinterland, so which may affect the infrastructure and cause very high damages in the hinterland. Actually, one big issue for the dunes and barrier islands that also they protect against the flooding, and one important thing as well is environmental consequences of flooding. If we have a flood, this means that we have a flooding of salt water, and this salt water may infiltrate here. Here we say that the flooding may cause here infiltration and of salt water, causing the so-called vertical saltwater intrusion. And this vertical saltwater intrusion actually is affecting so much our coastal aquifers and increase the salinity of this groundwater, and this affects actually increases the treatment costs of groundwater, and this becomes very highly important in countries like Sri Lanka, like India, nowadays in Egypt, for example. Even in the north of Germany, we have many coastal dunes and barrier islands that may be affected by climate change, and then we may have breach, as we see here in the photo, and then following the breach, we may have vertical saltwater intrusion. So at the end of the day, dunes and coastal barriers has very important or play very important roles in mitigating flooding and also environmental consequences of flooding. If we would like to speak about the erosion of natural coastal barriers, so we would like here to speak about the driving processes, and mainly the main driving process is the hydraulic load. And if we would like to speak about the hydraulic load, then we have the waves, and we will have also combination of wave and tide and surges. And in this case, we may divide the situation to four situations. We may have just the swash regime here, as we see here. This is the wave. The total water level here is still under the toe of our barriers. Then we will have here only beach erosion. But if the storm tide level, the combination of surge, tide, and wind waves are more than the toe of the barrier, then we will start to have impact of wave with the barrier, and we will have here seaward dune erosion or barrier erosion in general. If the water level increases more, then we will have the overwash or overtopping regime, and this will start to cause erosion in the landward side of the barrier or the beachward side of the barrier islands. Then, with more increase of the sea level during a storm, we may have the inundation regime. This is full overflow of water, and this is actually become very destructive of the dune system. So so at the end, we can say that the regime of erosion will depend on the relation between the total water level and the barrier crest and toy. And then, yeah, if we would like to go deeply to the processes, we will find that we have here the short waves, and yeah, we will have short waves, also called wind generated waves. And the problem is that usually these wind generated waves are combined by infragravity waves. This kind of long waves. They started to propagate and they become higher in height near to the beach as compared to the short waves, especially in case of dissipated beaches. So the total water level becomes higher due to the infragravity waves. And then in case of a storm surge, so we will find that the total water level now is higher than the toy of the barrier, and we will start to have impact of the water with the dune, which will cause erosion and maybe a breaching of our dune system or barrier island system. So we may here divide the erosion to seaward erosion. Here we say that our dune system is eroding from this part, and here we have deposition. Then we have narrowing of the dune volume here, so we become more vulnerable to flooding. And this is in case of the total water level is still under the crest of the dune. But if the water level is higher than the crest of the dune, then we will have directly here landward erosion. So the idea is that all these regimes in the reality may take place together. So as we see here in this photo for the fire islands in the United States, we will find that here we started with seaward erosion, and then some breaches are initiated due to with this overwash openings here, and one of the breaches developed here. So our main concern here with this study is to understand why a breach takes place here and not here. So what are the governing processes that let a breach take place here? Is it only the hydrodynamic? Is it the topography and bathymetry of the dunes system and the fronting bathymetry? So we thought about this, and we found that also soil properties may play a role. In order to investigate this role of the soil properties, we try to actually understand how the waves, the hydrodynamics will interact with the morphodynamics and also with the soil properties. So if we would like to understand how a breach will initiate, then we will have to collect data for the longshore variability of the hydraulic load in terms of waves, tide, and storm surges. And also we have to collect data about the longshore variability of the barrier topography and fronting bathymetry, like the four dune variations alongshore, and also the subaqueous variation of bathymetry. The third very important parameter which this study actually tried to account for is the longshore variability of the soil resistance to erosion. Which actually makes some portions of our dune system or our coastal barrier system more vulnerable to erosion, and this is we actually based in the, as will come later, we found that permeability is the main parameter that affects the dune erosion or coastal barrier erosion. So if we have these three informations and we would like to investigate where a breach will take place, this depends on if we have longshore variability of the topography, but we don't have longshore variability of the soil properties, then breach initiation is just a function of the hydraulic load. But if we have, besides the longshore variability of the hydraulic load, a longshore variability of the topography, then the breach determination to determine the location of the breach, then we will have to account for both of them, the longshore variability of the load and the longshore variability of the topography. Then we come to the point, if we have variations in the soil resistance to erosion, then we will come to very complicated situation. This is the level 4. So starting from here to here, we will find that the complexity of analysis becomes very high, and yeah, this is because of accounting for soil properties. So now one may ask how soil properties may affect erosion. So in the reality, many coastal erosion studies have found that coastal erosion is always overestimated, especially when we use models like XPeach. And for this purposes, some studies like McCall 2010, he introduced an artificial limiter presented by this line here, and he said, okay, in order to make our numerical models work, we would like to limit the flow velocity in the sediment transport analysis. And based on that, he assumed that the effective shell shell parameter is equal always to 1. This means that the flow velocity for sediment transport will be always around 1. And based on that, this is actually a very this is a limitation of the model which need further investigation. Why we need to have such artificial limiter? Actually, we did a study in 2017, and we introduced the concept of soil resistance, and we said, okay, the initiation of sediment motion is totally different if we have very high flow velocities as the situation during storm surges. And we introduced the concept of soil resistance, and based on that, we tried to amplify the Shell's curve as we see here. This is the original Shell's curve, and we try to amplify the critical shell number in order to justify why we have overestimation of the erosion with models like XPeach. But we found recently that the latency theory of Van Rey 2010 describes better why we have always overestimation with conventional sediment transport formula implemented in XPeach. Actually, if we have very high current like this, we may find that, okay, the sediment transport is no more grain by grain transport. It is the so-called sheet flow transport, and in order to have such sheet flow transport, we need to dilate the soil, and such dilation actually makes such hydraulic gradient here, and dilation of the soil is the expansion of the soil, and this expansion makes rearrangement of the soil particles here and produce inflow of water, and this inflow of water depends on the permeability of the soil. So this actually makes the initiation of sediment motion here totally different, because here we have the latency or sheet flow regime, not a grain by grain sediment transport as was always expected with such models. So usually with very high flow velocities as the situation during storm surges, we will have sheet flow, and this will need to account for soil properties like permeability and also porosity. How can we account for this? Actually, right now there are two models, two numerical models in the literature. One of them is by Van Rey 2010, and he said that, okay, Shell's parameter can be amplified based on the value of the permeability here and porosity. And some other parameters, one of them is the variation of the bed level, and this variation of the bed actually it's called the flow, the erosion velocity here, and this erosion velocity depends on the flow velocity. So here, this kind of model here by Van Rey introduce or calculate here the resistance. We call it resistance by Van Rey, and we find that, okay, this resistance is just in order to calculate the amplification of the critical shield parameter, we find that we can multiply the shield's number by the resistance plus 1. So, and this actually we found that from a study by Moore and others in 2021, there is another model, and actually it's also based on the permeability of the soil. So this means that permeability of the dune soil is very important in the analysis, especially with very high flow velocities. Here we can find this. If we have here the permeability in the horizontal axis here, and here we have the implications of the shields number, we will find that with very low permeability values, we will find that especially with high erosion velocities, we will find that the shields parameter need to be amplified like by 5 order magnitudes, especially with very low permeability values. So permeability values becomes very important with very fine sediment and also with very high flow velocities, and this is something which was not considered before in the analysis of dune erosion. And this study actually implemented this, but also in spatially varying fashion in order to account for longshore variability of dune erosion. So in this study, we tried to make to understand how permeability could be reduced. Actually, in order to reduce the permeability of the dunes, we can actually make a kind of compaction of the dune. This is reduce the porosity, and based on reduction of the porosity, if we reduce the porosity here based on this Karman equation, we will find that reducing the permeability here will reduce. Reducing the porosity here will reduce the permeability. But another very effective reduction of the permeability of the dune in order to find a natural-based solution to dune erosion is to actually mix the dune material, the sand, with some fine materials like other sand, but very fine, or to actually, as we found that the most effective solution is to mix the sand with bentonite. Mixing the sand with bentonite, this is a very swelling soil. It's a kind of clay, but very swelly, and this actually closes the voids and makes the permeability very low, as we see here. This figure describes the relation between the volume bentonite content and the permeability, the relative permeability, and we find that once we increase the content of bentonite, we will find that the permeability is reducing so much. And we tested this. We found that this is with many soils is still valid. So adding bentonite to sand, or mixing bentonite to our dune system may reduce the permeability so much, and in this way we are reducing the coastal erosion so much, and this is the idea of this natural-based solution. Another way is to reduce the porosity, as discussed before, and we find reducing the porosity could be through the consolidation, the natural consolidation due to loading of the dune system, or by mechanical compaction. If we consider the mechanical compaction, so we'll find that during the inflow of water among the sediment, we will find that this is the situation before compaction, and after the compaction, many passes of water will be closed, and this makes the permeability, as reduces the void ratio and the porosity, and also the permeability according to this formula. So this is actually another way. So we introduce here either to mix our sands with bentonite. This is a very effective solution, or to consider mechanical compaction. And especially for the project of sand dune restoration or such projects, we need to account for such solutions. They effectively reduce dune erosion. So here we make a summary of this. A natural-based solution, we will find that we can introduce the mechanical compaction or the natural consolidation due to loading with more sand that comes due to wind effect or due to hydrodynamic processes, or we mix our sand with finer soils, or the most effective is to mix our sand with the dune sand with bentonite fraction. In this way, all these situations or the solutions are reducing the permeability and reducing the erosion. In order to investigate this, actually, we extended the X-pitch model in order to account for spatially varying permeability. And here, this is the domain of X-pitch, the mesh of X-pitch. This is just a schematic representation of how we account for spatially varying permeability in X-pitch. This was a model before extension. It can account only for a single value of permeability. This means that along shore uniform permeability. In our extension to the X-pitch model, we account for spatially varying permeability, and in this way, the model is extended in order to account for spatially varying soil resistance to erosion. In this is a case study. We have here this three-dimensional. This is a synthetic case study because it was not possible to find a real case study that actually include hydrodynamic loading and also variability of the topography of bathymetry and also variability of soil properties. So. Actually, in this study, we introduced this synthetic case study. We assume here that the dune is uniform in terms of topography, but we apply sometimes hydraulic load with short crested waves and sometimes with long crested waves in order to investigate. Here in this presentation, we only apply long crested waves just to say how the permeability variation along shore will affect the erosion. We introduce this variation of the water level as a storm surge. We apply it, and then we apply a Jones swap spectrum with significant wave height 1.75 meter and a peak period of 6.6 seconds. So. Here we vary the permeability in the dune zone here. This is the dune zone. This is the dune zone here, and we vary the permeability along shore. Here, the permeability is very low. Here is a middle permeability. Here, this is high permeability, and then again a low permeability and very low permeability. So, in order to show this, we can look at this video here, and we will find that at the locations of the very low permeability, we have initiated breach here, and we will find also that the dune erosion, this can be actually visible more from a figure which will come now. So we'll find that the breach is initiated here. Here we have different erosion than here. So the dune is eroded more at the location of high permeability, and the erosion reduces with the lower permeability. So here we assume that this part of the dune has 10% bentonite. We mixed the dune sand with 10% bentonite, here with 6% bentonite, here with 0% bentonite. And again here 6% and 10%. And we find when we mix our dune system with bentonite, we find that the erosion is reducing so much, especially with 10%, because of the very low permeability. So this means that erosion of dune system and breaching mainly depend here in this case on the permeability value. With very low permeability values, we will have less erosion. And this is the idea. So if we would like to consider the reduction of the porosity, we started from this point here, and we reduced the permeability as a porosity from 0.4, assuming that our dune system will be compacted or consolidated, and the porosity will reduce from 0.4 to 0.3. And we find with the 0.3 that the erosion is reducing more. Even the breach here, which occurred here, was significantly reduced in volume. And the dune erosion at the locations of 6% bentonite, which is has middle permeability here, is still more efficient, but 10% bentonite with very low permeability value, we will find that the erosion is much less than the situation here. So, but we find that when we compare this with this zone that we find that especially if we would like to look at the differences of the bed, we will find that the porosity values has very important role in the locations of low permeability, and this effect is reducing with the low permeability, and this becomes here. There is no difference here at this zone, zone C, because of the low permeability. So we can find here that reduction of porosity is very important at locations of high permeability, and actually has no effect at the locations of low permeability. So as a summary of this presentation, so we find that at high flow velocity regimes, like the situation during storm surges, that sediment steering and transport is no longer a grain by grain pickup, but it is actually determined by the so-called dilatancy reduced erosion, which is mainly a sheet flow erosion. So the second conclusion is that permeability of barriers determines to a large extent the degree of soil resistance. Soil resistance is actually a function of the soil permeability. This parameter was not considered in previous studies because of the lack of knowledge. And here we introduce the permeability. We are like making alarms that place in soil in coastal erosion studies. Permeability and other soil properties are very important to account for such variability in order to reduce the uncertainty during expecting or predicting where breaches may take place. So in this study, we extended the XPitch model in order to account for spatial variability of soil properties, spatial permeability, and we found that the model is doing a good job and actually is helping us nowadays to investigate where are the most possible situation for breaching. So this actually comes to another point, that reduction of soil porosity or permeability represent actually a natural based solution in order to reduce coastal erosion, and the reduction of coastal erosion may prevent the breaching and again the flooding, and this will save a lot of lives and economy and will save our infrastructure. I think I'm done. I thank you very much for your kind attention, and please email me in case of any question. I am Sabir Said from the Technical University of Punjab. As I introduced myself, here is my email. Please email me in case of your question. And now I'd like to introduce the next speaker, my colleague Carmelo Maximiliano. He will speak about the role of coastal dunes. Yeah, thank you very much.
Thank you, Saber. Sorry for interrupting. I just wanted to remind you to leave your questions in the chat here on Teams or Facebook or YouTube, wherever you are watching this webinar. And also, please don't forget to fill the attendance list if you would like to get the certificate for participation. So I'll leave it to Carmelo. Thank you. We are watching your screen, Carmelo.
Okay, can you hear me?
Yeah.
Okay, thank you for the presentation. Well, I'm going to talk about the role of coastal dunes and vegetation in coastal protection. But before starting, I would like to thank Valeria, Rodolfo, and all the people involved in the organization of this webinar. And I will put a special emphasis on the role of species of plant functional drainage, okay? So first, what are coastal dunes? Coastal dunes are aeolian bed forms developing where the transporting competence of wind is impaired mainly through the interaction with the vegetation. Here in this figure, I will simplify how this process is originated. Sand could be stored here or along the surf zone profile. Here, forming sandbars or being transported along shore, then waves transport this sediment to the beach where the wind and the sun dry the sand, and then wind transport the sand inland where the plants play a major role. Plants act as natural obstacles, they accumulate sand, and it's very important to mention that these plants are highly relevant because they can tolerate sand burial. Even this process can stimulate plant growth, and then plants can continue promoting the dune development. So here is the origin of the coastal dunes, and here are some examples. These are 4 dunes located in La Mancha, Veracruz, a beach that is located on the central coast of Veracruz. Okay. Very diverse in terms of geomorphology and also in terms of biodiversity. They support many species. And since an anthropogenic approach, coastal dunes are highly relevant because they provide many ecosystem services that are highly relevant for human well-being. For example, I think 2 of the most important are recreational activities. They are very important for tourism. Systems that are like above versus ocean. So the interaction of coastal dunes and beaches with the storms is a natural processes. We have to highlight this because sometimes people see this process like a problem, but this is only since an anthropogenic approach. And in fact, the impact of storms on coastal dunes and the erosion they induce and floods are important processes to keep biophysical processes. Saber it simplified these processes in its presentation. I would mention once again, but only slightly. During a storm impact due to the storm surge and the increasing waves can break on the highest part of the beach and dune profile, and inclusive they can break on the exposed face of the beach. So the sediment could be transported inland or could be transported to the sea. If the conditions are not extreme, the sediment could be forming a sandbar, and when calm conditions prevail, the sediment will be on the beach and dune profile once again. Here I am simplifying these processes with a natural beach that is on the central coast of Veracruz. This beach and dune profile was impacted by a winter storm, but since the sediment budget was not affected, the sand is being transported once again to the beach and dune profile, and plants are promoting the dune development. Okay. And as I told you, these are natural processes, but the big problem is that human really loves to live near of the coast, as we can see in this picture. Okay, the coasts are densely populated, and then human interests and lives are threatened by natural and human-induced processes. These are pictures or photos to exemplify the problem. So instead of have a natural scar here, we have the wave attack directly on the human infrastructure, for example. And the problem is getting worse because some long-term processes such as sea level rise, and for example, it is predicted that more frequent major storms will impact the coast. And this is another problem. Human is interrupting the sediment transport along the coast. And this is the main point of this webinar. The nature-based solution has been highlighted as important element to protect the coast in the literature, maybe since 50 years ago. Maybe with another definition, but the main point is that coastal ecosystems or working with a natural process can contribute not only to mitigate the ocean hazards on the coast, but also to develop adaptation strategies. In this scheme taken from Temmerman et al. 2013, we can see an example of a coast that maybe due to human activities is facing some problems like land subsidence, wetland degradation, and maybe there is not sediment availability and dunes are not functioning well. So when a storm hit the coast, the city could be very threatening. However, if we have the ecosystem working, if we work with natural process, maybe we could have a coral reef, seagrass beds in this part. If wetlands are in a good, if wetlands are good, they can promote the sedimentation that is like a natural processes to deal with sea level rise, for example. And then if we have sandbars and beaches and dunes, the impact of the storm would be lower. And the ecosystem that I am interested, of course, is coastal dunes. They are the first terrestrial defense against storm impact. And they are very important because it has been demonstrated that they can reduce property damage. Additionally, coastal dunes, as other coastal ecosystems such as wetland and mangroves, are very important natural buffers because they can deal or they can be adapted to wind and wave climate. They can migrate landward or seaward in response to the littoral conditions, okay? But before to promote these alternatives, we have to investigate a lot. We have to understand what are the main processes or the main features that confers beach and dune resistance. For example, if we know that coastal dunes act as buffers, maybe it would be a good idea to increase their resistance to prevent erosion and mitigate floods. But many features are related with this process, and the amount of sand to be eroded during a storm depends on the storm-related features, depends on the beach and dune profile. Additionally, Saber talked about the importance of the sediment characteristics, and the element that I am interested in is vegetation. Okay, first, it was like anecdotal, the hypothesis that the plants could mitigate the impact of waves. It was hypothesized many years ago that above ground plant parts interact with waves and act as a shield to protect the sediment, while below ground plant parts promote the resistance of the non-sediment cohesive, sediment. So here we have a figure taken from Figgin et al. 2050 to exemplify this interaction of the plants when the waves are reaching the exposed phase of the dunes, so they can mitigate the wave impact. And it's very important to mention that plants not only act during the storm, the protection that they can provide is like an accumulative processes, because as you can remember, I mentioned that plants are the important element to promote the dune development. So they promote the growth of the dune barrier. Fortunately, nowadays is not anecdotal anymore the role of plants. Many experiments have been conducted to investigate how plants can mitigate erosion. And first, for example, Kobayashi et al. 2013 used cylindrical wooden dowels to simulate the plants on the dunes. They create their simulated dunes, and in a wave flume, they exposed these dunes with the plants to storm conditions. Authors found the presence of the dowels could reduce the forest slope escarping and initially prevented the overtopping. However, when the overtopping was initiated, the plants continued reducing the overwash. Later, Sigren et al. 2014 used real plants to test this hypothesis. In fact, they used the grass Sporobolus virginicus, and they exposed their dunes to storm wave conditions too, as Kobayashi. And they observed that effectively plants reduce erosion and dune scar. Later, Silva et al. 2060 used the species Hypomea pescapre, that is a pantropical species, and they test new variables. For example, they test the role of plant density. That is very important because we know that plants are not like fixed elements. They have some important features that are changing in time and space. However, they did not find a clear relation among the plant density and the sand volume to be eroded, but they test the hypothesis that Hypomea effectively could mitigate erosion. Okay. It's very important to mention that in field conditions, in a study performed by Charbonneau et al. 2070, they found that the protection that plants could offer to the sediment is species specific, and at the same time, it contribute to make some questions. For example, dunes are commonly covered by more than one species, as we can see in this picture. Here we have 2 or 3 species coexisting. So the next questions emerge. For example, does an increase in plant functional richness covering the dune mitigate erosion? And another question is that, are there species and species combinations that better protect the sediment? So we decided to evaluate the role of functional richness. We decided to make some experiments, and we selected 3 pantropical species that are Hypomea pescapre, that is a railroad vine, Sesubium portulacastrum, and the grass Sporobolus virginicus. Here is a picture of the 3 species coexisting on the central coast of Veracruz, and they are well distributed on the backshore and on the embry dunes that are the parts that are more frequently in contact with the swash or the wave attack. Okay, so we performed the experiments in a wave loom that is located at the Institute of Engineering here in Mexico, and we created these artificial dunes. This is our experimental designs. So in this experiment, we test erosion when vegetation was void of plants. We test erosion when the dunes were covered by only one species, Hypomea, Sesubium, or Sporobolus. We test the combination of 2 species, and we test the combination of 3 species. I forgot to mention that our hypothesis is that since species richness or coastal ecosystem services could be better if we have more species, then we hypothesized that more species on the dune with different structures could better mitigate the erosion. Here are the number of replicates. On the wave loom, we exposed the dunes covered by these treatments to storm waves with a spectra of Jones-Swap. The significant wave height was 20 centimeters. The peak period was 2.21 seconds, and the storm lasted 40 minutes. It's very important to mention that the storm lasts 40 minutes, but we measure the volume of sand eroded every 5 minutes. We decided to make this first to compare our experiments with the literature and to go beyond the experiments that have measured erosion during only 20 minutes. So the response variable was erosion, and to evaluate or to compare erosion, we performed a mixed effects model in which the treatments that are species or species combinations and the time were defined as fixed factors, and time was modeled across the state as a random factor to prevent the pseudo-replication, to deal with the repeated measurements. Okay, the main findings. Whereas we can see in this picture here, we have the no vegetation treatment and all the rest of the treatments that are with one species, Hypomea, Sesubium, and Sporobolus, and the possible combinations. From the 0 to the 20 minutes, we can observe that the treatment with no vegetation was greater eroded in comparison with the treatments with plants. Okay, it's very important to mention that Hypomea was the species that had a lower erosion. However, at the end of the experiment, it's very important to highlight that not all the plants or species combinations protect the dune. For example, we can see here that the combination of Sporobolus virginicus with the species Sesuvium portula castrum and the combination of Ipomea pescapre with Sesuvium portula castrum suffer more erosion than the control dune, that is the dune void of vegetation. While Ipomea and the combination of three species, the combination of Ipomea with Sporobolus, protect the sediment. Sporobolus suffers almost the same erosion that the treatment with no vegetation. And of course, when we test statistically these effects, we found that it is statistically significant. Okay, this is the significance. And here are the combinations or the comparisons. We can see that the non-vegetated treatment was almost significant different with all the treatments with vegetations. And it's very important to see that since we are interested in the functional richness, we can see that this treatment did not differ only with the non-vegetated treatment. So we decided to test what happened in the 5 minutes interval. So we extracted this information, and for example, at 5 minutes we can see that the non-vegetated treatment was eroded more than the treatment with Ipomea pescapre. The erosion was almost the double. However, the treatments with vegetation did not differ among them. At the end of the 5 minutes, we can see that Ipomea pescapre mitigates the erosion, and the non-vegetative treatment was greater eroder than this treatment. Okay. Why did we find this? The explanation is because of the architecture of this species. First, we confirmed the hypothesis and the findings of Charbonneau et al. 2017, who found that protection is species specific, and we find the same. Ipomea was the species that better protect the dune and the sediment versus storm waves. And this is because Ipomea is a railroad vine that grow on the dunes, and it covered the dunes like a big carpet, while Sesuvium portula castrum also is a semi-air creeper. However, this species did not cover all the dune, and Sporobolus virginicus is a grass that leaves are far from the sun surface, so it is not good to mitigate erosion. Here we have some pictures to exemplify here this. As we can see in this picture, the architecture could be relevant in mitigating erosion. For example, during the experiments, we observed that this species, Sesuvium portula castrum, lose their stems and their leaves. They were losing, they were brave by the wave action. However, Ipomea pescapre resists the wave impact, and Sporobolus did not resist the wave of Sporobolus virginicus. Additionally, we can see here that leaves from Ipomea are well grouped, while the leaves of Sesuvium portula castrum are not well grouped, and in fact they are far from the sun surface, so they can not mitigate very well the hydrodynamics. Additionally, the leaf area is another important factor. We have a greater leaf area for Ipomea pescapre in comparison with the Sesuvium portula castrum and Sporobolus virginicus. And despite Sesuvium portula castrum has a greater number of leaves, as we can see, they are not grouped, as I told you, like in Ipomea pescapre. So this could be the explanation only also to demonstrate why the species combinations sometimes did not function very well, because if we have competitions for the space among these species, Ipomea pescapre lose cover, and maybe it could not be okay for coastal protection. Okay, the main conclusions is that plants contribute to the development. That's a good ecosystem services. Plants protect the sun and retarded erosion. And the protection is species specific, so we have to be very careful of what species we are promoting to protect the coast. And also, we find very important that there are combinations of plants that better protect, or inclusive that there are combinations of plants that did not protect very well the dunes. So we have to be careful with the restoration plans, for example, because if people think that all the vegetation can protect the coast and they use the wrong species, it could be not very good for coastal adaptation strategies, for example, in this case. Additionally, it's very important to highlight that I don't want to say that feeds the dunes with vegetation is the only option. In fact, some dunes have to be not feeded because the sediment transport has not to be interrupted. But these findings contribute to demonstrate that the presence of plants in coastal dunes could mitigate erosion in some circumstances. So thank you for the institutions that have helped me with support, and with my collaborators, Maria Luisa Martinez and Rodolfo Silva, that are my thesis advisors. And that's all. Thank you. So to continue the program, the next participant is Nadia Zamboni. She is going to talk about mangroves.
Can you see now?
No, you're not sharing your screen.
Not yet?
No. Yeah, we can see it now.
Yes, I know.
Yeah, I guess I hear you a bit. Maybe you can increase your volume on your computer.
Okay. I will try to be louder.
Thanks.
Okay, so I will start. Well, hello everybody. First of all, I want to thank all the organizers of this webinar for the invitation and the opportunity. My name is Nadia Zamboni, and today I will present to you this study titled Mangroves, Blue Carbon and Coastal Protection Services, a case study from Northeast Brazil. This study was developed during my PhD studies in Federal University of Rio Grande do Norte, under the supervision of Dr. Adriana Carvalho and the collaboration of several specialists. Well, as we already know, mangroves are very productive and valuable ecosystems. They provide with several benefits that assure human well-being. And through the delivery of various provisioning, regulating, supporting, and cultural ecosystem services. Besides, due to the high carbon storing capacity, mangroves are also known as very important coastal blue carbon systems. They contribute with the climate change mitigation through the reduction of global atmospheric carbon by sequestrating and storing carbon above and below ground, and also through the soil carbon retention. However, mangroves suffers from the impacts of deforestation, land conversion, urbanization that promote the release of carbon to the atmosphere, turning mangroves into emitters of carbon and reducing the blue carbon capacity. Thereby, they increase the global warming and provoke high global economic costs. Another important regulating ecosystem services from mangroves is coastal protection. They act as barriers against floods, erosion, and natural threats to coastal populations, dissipating waves and currents through a very complex root structure. They also protect properties and economic activities. However, as I already mentioned, they suffer from the impacts of human threats such as deforestation and land use changes, and the effects of climate change such as sea level rise. So these impacts provoke a coastal squeeze phenomenon, limiting the expansion of mangroves. Although Brazil has the second largest mangrove in the world, the second largest mangrove area in the world, it suffers from the effects of climate change and anthropic pressure. That's why it's very important to study the benefits through ecosystem services provided by these systems. Besides, there is a scarcity of studies valuing and quantifying ecosystem services from mangroves in Brazil. So for this study, we tried to analyze these two important regulating ecosystem services, the blue carbon and the coastal protection services. On the one hand, for the blue carbon analysis, we evaluate and forecast the effect of land use conversion from 2017 to 2050 on the dynamics of mangrove forests and on changes in the provision of blue carbon. We also estimate the current economic value of blue carbon. On the other side, for the coastal protection analysis, we assess the vulnerability and temporal changes in the coastal landscape, measuring erosion and accretion rates on the coast and estimating the losses and economic cost of coastline retraction in the long term. Mangroves situated in this study area are located along 70 kilometers of the coastline in the northeast region of Brazil, situated in the state of Rio Grande do Norte. These mangroves grow in stretches and directly connected to the sea and associated with different geoenvironmental units such as tidal flats, fixed and mobile dunes, interdune depressions, estuarine fluvial plains, and beach barrier islands. The most dominating species of these mangroves are Rhizophora mango, also known as the red mangrove, and Aphsenia showeriana, also known as the black mangrove. In this region, we also observe intense erosive processes occurring. And there are also tectonic faults that determine, in part, the dynamics of the geomorphology of the region. We can also observe that there are different economic activities developing in the region, but there are two activities that stand out and negatively affect mangroves and their natural processes. One of them is salt extraction and the other is shrimp farming. Talking about the methodology of this study, we start with selecting satellite imagery, multispectral and radar images from 1999, 2007 and 2017 in order to have evidence of historic changes in land covers through time. And then we apply some correction and processing steps like using different software tools such as NAV, ArcMap, ArcGIS, and ENVI. Once we have these images, we proceed with two different ways or two different methodologies, one for the coastal protection analysis and the other for the blue carbon analysis. For this second one, first we fusion multispectral and radar images in order to have hybrid images that allow us to have clearer visualization of the mangrove species and differentiate them for other non-blue carbon classes. So we classify and verify these images by using different literature and the support of experts. And once we had these land use land covers, we estimate historical conversion rates from mangroves to other land use land covers, such as salt streams, salt ponds, and shrimp farms. Once we have these conversion rates, we generate two different future scenarios for 2035 and 2050 by using the scenarios generator tool from Invest. Then we quantify and value the blue carbon service from the current and the future scenarios, and some of the estimates were carbon stocks, carbon emissions, net carbon sequestration, and net present values. The inputs we obtain from literature and fieldwork. On the other side, for the coastal protection analysis, we only use multispectral images. And after we do the correction and processing steps, we proceed doing the multi-temporal analysis of shoreline changes. Some of the estimates using the digital shoreline analysis system was the shoreline change envelope, that is the distance between the closest and the furthest line from a baseline in a period of time. Then the net shoreline movement, that is the distance between the oldest and the newest line in a period of time. And the linear regression rate, that was just a regression analysis in which we obtained the shoreline change rate, accretion and erosion rates that lead us to have a forecast of the changes in shoreline for the year 2026. Then we apply a coastal vulnerability modeling by using the coastal vulnerability model from INVEST in order to, in two different situations, with the presence of mangroves and the absence of mangroves, in order to observe the contribution of mangroves as coastal protection barriers. Some of the inputs in these models were geomorphology, different coastline types, natural habitat, relief, wave exposure, and shoreline change rates that was an indicator of sea level rise. Finally, we did some economic estimations measuring costs due to coastal retraction. Next, please. Among the results of blue carbon analysis, observed that in a 33-year scenario of conversion from mangroves to other land covers, we observed that total mangrove areas could decrease 34% by the year 2050, while salt ponds and shrimp farms could increase 13.5 and 31.5%. And we noticed that salt ponds seems to be the economic activity that contributes the most to the loss of mangrove species, at least in the first 18 years, from 2017 to 2035. However, shrimp farms also show a high contribution of the loss of mangroves. Next. The total amount of carbon stored in these mangroves could decrease 22.2% by the year 2050, and this confirmed the loss trend of total mangrove area. Much part of this reduction, about 74%, could come for the loss and the reduction of total carbon stock from black mangroves, Apsenis showeriana. Although we observed this reduction trend in the total amount of carbon stock, we also observe an increase in the average value of a carbon stock per unit area through time, but in an uneven distribution of values, and this could be due to the distribution of the two different species. The red mangroves are more located in core areas, while the black mangroves are distributed more in fringe areas, more connected to the economic activities that are affecting mangroves. Anyway, we observe that these mangroves act as carbon sinks. They can sequester about 17.3 tons of carbon per hectare per year. However, it could become carbon emitters if they continue losing area. And this could be observed in the carbon emissions values, especially from 2017 to 2035, reaching a carbon emission of about 1,000 tons of carbon dioxide per hectare. Next, please. So the blue carbon value that we observe here per unit area in these mangroves apparently seems to be lower than the economic benefits per unit area observed for shrimp farms and salt ponds. However, it's very important to consider extrapolating this blue carbon value to the entire area of mangroves in Brazil. And this value could outweigh the benefits obtained from these other industries that in turn benefit just a very restricted group of people. Next, please. Well, among the results obtained from the coastal protection analysis, we observed that from 1999 to 2017, there is a shoreline change rate of about 1.2 meters per year of retraction of the shoreline. And 44% of this shoreline show relative stability, while 20% show low erosion rates, 13% showed high erosion rates, and about 23% showed some sediment deposition. We also observed that 79% of shoreline showed a high amplitude with an average value of 146 meters. And 48% of this shoreline showed high negative mobility with an average value of minus 20 meters. Next, please. Well, so based on these erosion and accretion rates, we could forecast changes in coastline for the year 2026. And we observed that the coastline is expected to have an average change of minus 9 meters by the year 2026. And much part of the erosion areas are located in barrier islands and in sandy spurs that are facing the open sea, while the accretion or the sediment deposition areas are more located in the mouth of rivers. Next. Regarding the coastal vulnerability analysis, we observed that 40% of the coast is under moderate high vulnerability with the presence of mangroves. But if we remove these mangroves, this moderate high vulnerability could go up to 60%. And much part of these vulnerabilities are situated in estuarine areas and tidal channels. So these results showed us the importance of mangroves as coastal protection barriers and how they can reduce vulnerability of the coast. Next. A quarter of the total population exposed to coastal risk is in a moderate high vulnerability currently, but it could increase in half the population if we remove mangroves. Besides, we observed that between 1999 to 2017, there is a loss of land of about 141 hectares, equivalent to an economic loss of almost $15,000. An additional loss of 63 hectares by the year 2026 could sum up an economic loss of $22,000. We also observed that a future cost of mangrove restoration, if we lost mangroves in an equivalent area that we lost land, it could reach about $171 million. So it's a lot of costs. Next, please. So some of the conclusion of these studies were that mangroves in the northern region of Brazil act as carbon sinks, but could become emitter if high impact human activities, such as salt extraction and shrimp farming, continue to expand. Besides, blue carbon benefits from mangroves is available to all people, while economic activities that reduce mangroves generate economic benefits to a restricted group of beneficiaries. Estuarine areas are more vulnerable due to the effect of rising sea levels and human activities. And we also observed that coastal vulnerability is high, about 40%, and can reach 60%, exposing half the local population to risk and high costs. So this shows us the importance of mangroves in the northern region of Brazil and all Brazil as carbon sink and as coastal protection barriers. Next, please. So what is needed? Mangroves area benefits are underestimated in this study because we only evaluate coastal blue carbon and coastal protection services. But we need to evaluate to quantify and value other market and non-market ecosystem services in order to subsidize spatial planning and design strategies in these mangroves. We also need restoration of lost forest area measures. We need a limitation of the expansion of high impact activities such as the ones that I mentioned, and strengthens the laws that protect mangroves because Laws that protect mangroves in Brazil are laxist. We need more robust and participative conservation strategies are necessary in order to avoid more mangrove forest downsizing. And the application of ecosystem-based coastal adaptation planning supported by vulnerability temporal and assessments also are very important. Next. Well, I want to thank everybody for assist, and this is my contact if you have any questions or suggestions. So thank you very much.
Well, I think we will have to continue with the next speaker. So, are you ready to continue?
Yeah.
Yeah.
Yeah,
Well,
I'm ready.
Thanks, Fernando.
I'm going to start. We are going. Hope that that is okay. I'm going to share my screen. So let me see. If you see it, you see the presentation?
Yes. Yes.
Is everything okay? Oh, okay. Okay. Hello everyone. Thanks to the organization for this webinar. To Valeria, Rodolfo, it's a pleasure to be part of this webinar with great colleagues. My name is Fernando Lopez. I'm a PhD student at the University of Cantabria and IH Cantabria. I'm supported from a scholarship from the University of Costa Rica and its coastal group IMARES. Today I'm going to talk about a new numerical tool for quantify wave attenuation in salt marshes, which is part of my PhD research that I'm doing with Maria Massa and Javier Lara. Well, I'm going to give you an overview of the presentation. First, I'm going to start with a brief introduction. Then we'll talk about SWAN and how does this model quantify the wave attenuation. Next, we will talk about the drag coefficient, which is part of the drag force modeling. And after that, I'll give you a new approach for quantify wave attenuation based on biomass and how it was implemented in the SWAN model for at the end give you some conclusions. So, well, salt marshes are ecosystems located in the intertidal zones. As you can see in this map, they are located in Arctic and temperate zones. This kind of vegetation provides ecosystem services such as nursery habitat for animals, water filtration. Also, they collaborate to the nutrient cycling and carbon sequestration. They provide coastal protection, which is the ecosystem service of our interest in this moment. When we talk about coastal protection, we can talk about wave attenuation. In last year, researchers have been interested in knowing the wave height decay through vegetation and how to quantify it in a precise way. In this presentation, I will give you some details of a new implementation, new numerical tool for evaluating the coastal protection service. We have been looking for a tool based on a predictive approach without the need of calibration, and that can be applied in a generalized way for several salt marshes species. First, the studied scale must be defined. We can consider the plant wave interaction only or the meadow as a whole. Here is where we use field scale or mesoscale models. They are based on two approaches: bottom friction enhancement, where the vegetation is considered as an additional friction by a friction coefficient, or when we talk about the energy dissipation due to the work carried out on vegetation. Some numerical models, SWAM, are based on this approach. What is SWAM? As many of you know, this is a full spectrum third generation model which describes the wave spectrum propagation based on the spectral action balance equation. You have it here. I'm going to go into detail. But Suzuki et al. Implemented in the source terms the dissipation by vegetation. So they implemented this equation, and it was validated with some laboratory data and field data also, and it has been widely accepted and used in several studies. This implementation is based on Mendes and Lozada equation for random waves, which is an extension of Dalrymple et al. For equation for monochromatic waves. This formula is based on the energy conservation equation, which describes the energy dissipation produced by the drag force exerted on the vegetation. I will not go into details, but after developing this formula and doing some assumptions, we finally have these terms, which are the ones that SWAM resolves as a numerical model. So as you can see, this time average rate dissipation depends on vegetation parameters such as stem diameter, stem density, and plant height. Also, it depends on the drag coefficient, which comes from the drag force. This bulk drag coefficient, because considered whole the metal, take into consideration all the assumptions and factors that were not taken into account in the formula as plant motion, wave linear theory, and so on. Therefore, the reliability of the obtained results in the model are based on the right choice of this bulk drag coefficient. Also, additionally, as you can see here, we have a beta wave damping coefficient that describes the wave attenuation through the vegetation. You see that there is a function of CD also, the bulk drag coefficient, and the vegetation parameters. So in order to get accurate results of the coastal protection service that the vegetation provides, we should adequately calculate the value of CD parameter. But how do we obtain it? Well, there are two approaches. The non-predictive approach, which requires previously measured wave height in the field for calibrating the model, or by direct force measurement that is difficult to do it in the field. On the other hand, we have the approach that we call predictive approach. This predictive approach is based on non-dimensional numbers such as Reynolds and Kellogg-Carpenter number. We use the hydrodynamic and vegetation parameters, but at the beginning of the vegetation field or the seaward edge of the vegetation field, and we can predict how is going to be the wave attenuation through the vegetation. So these empirical formulas, some of them are shown here in this table. As you can see, for monochromatic waves, we have several, in this case, three formulations. Each of them, for each vegetation species, we have artificial seaweed. Also, they are derived from artificial or mimics of the vegetation. We have for Spartina an expression, for Juncus another expression, and so on. They have their range of application, as you can see here. For example, we have one expression for Spartina, another for Juncus. It's case-specific formulas. For random waves, I'll show you some of them. We have here Mendes and Lozada. They use artificial species. Yadav, their formulation was based on field campaign carried out on Louisiana coast. Anderson and Smith used artificial species. And you can see we have several ways to obtain this CD coefficient based on the non-dimensional numbers. Here I show you the pictures of these studies that they carry out. We have several plants with different geometrical properties, also biomechanical properties. Some of them are flexible than others. Here we have Puccinelia, and here is Spartina from Massa et al. 2015. Here we have the mimics from Anderson, and here in the field, the Spartina alterniflora. So, so far I have shown you this path or methodology for obtaining the wave attenuation results. First, we talked about field scale models or mesoscale models. Then we saw that in SWAM, Mendes and Lozada equation is implemented, and it depends on 3 vegetation parameters that you can see here: stem diameter, stem density, and plant height. And also the result relies on the CD coefficient that we can get it from empirical formulas for a predictive approach. And then we can get the wave attenuation or the coastal protection service provided by the vegetation. But this methodology has some limitations. The reliability of the results, as I said, depends on the CD value. The empirical functions we observe for obtaining CD are case-specific. They depend on the geometrical and biomechanical properties of the species. Also, the characteristic velocity and plant length for obtaining the non-dimensional numbers varies depending on the author. And it requires a lot of effort for measuring vegetation properties such as representative stem diameter and stem density as well. But now I want you to present a new methodology to quantify the wave attenuation, as you can see here in this scheme. And this methodology is based on the work done by Massa et al. 2015, where they evidence a relationship between the damping coefficient beta and the biomass. Perhaps, well, I'm engineer, so for us, the engineers, we are not familiar with this variable, but I'm pretty sure that ecologists and biologists know that this is a typical measure of vegetation mass per area unit. In this case, when we talk about biomass, we are referring to the above ground dry weight per area unit. So based on this idea, as the biomass as a key variable for quantified wave attenuation, is Massa et al. Carry out 96 tested in a waveflume for monochromatic and random wave each. They tested several hydrodynamics for quantify the wave attenuation through a vegetation field. They tested 4 species. As you can see here, Spartina, this is the biomass. We have Salicornia. They tested Salicornia, also Halimione, and Juncus. As you can see, they sampled vegetation from the lower saltmarsh to the upper saltmarsh. And all of them have different geometrical properties. You can see Juncus is taller than the others. Here you can see it in the waveflume. Juncus has approximately 70 centimeters. Spartina has 20 centimeters. This is the same water depth, as you can see. Also, they have different biomechanical properties. Some are more flexible than others. So at the end, they tested these 4 species and get a unique or a linear relationship between the beta coefficient, the damping coefficient beta, and a parameter code that they call hydraulic biomass. This linear relation, the coefficient AB depends on monochromatic and random waves, and this hydraulic biomass depends on 2 parameters, vegetation parameters, biomass or plant height, and also it depends hydrodynamic parameters such as wave height, incident wave height, and its corresponding period, with also the water depth, the incident water depth that we have in the vegetation field. So with this is a predictive way to quantify the wave attenuation through the vegetation. So from this work, we carry out a new implementation in SWAM. As you can see, this implementation only need as vegetation parameters the biomass and plant height. We also extended the implementation for taking into consideration the spatial variation of the biomass along the vegetation field. So distinct values of biomass can be considered. It is important to highlight, to emphasize that this implementation doesn't need a calibration parameter, and also that is a predictive approach, as I said before. It means we just need the hydrodynamic conditions at the beginning or seaward edge of the vegetation field. So a validation was carried out with the laboratory data from which the linear relationship was obtained. We did it for the 96 cases for monochromatic and random waves. Here I show you an example for Spartina. Here, this is the wave height, the distance along the vegetation, and in black points, we have the laboratory data, and the continuous line is the outcome from SWAM. You can see we did the validation for Spartina, Salicornia, Juncus, and Limone portulacoides. We have 50% density. It means that half of the vegetation field was cut down in the waveform. We have 100% density. Also, the water depth varies. We have 30 centimeters, 40 centimeters. The wave height also varies, and the peak period. So several hydrodynamics are reproduced here, and you see there's a good agreement in the monochromatic waves between the model, the outcomes from the model, and the wave measurements, wave height measurements in laboratory data, in the laboratory. Here we have for random waves, we did the same thing as you can see here for Spartina, Salicornia, Juncus, and Alimione. As you can see, we tried with different peak periods, 108 seconds to 408 seconds, also different water depths, and again, there's a good agreement between the model and the data in the laboratory. But well, at the end, here we are reproducing the wave conditions and the vegetation conditions for which the formula was derived. That's why we look for field data to try to validate the model. So thanks to Buick, we could have access to wave measurements carried out at Bat and Hellegat in Western Scheldt Estuary in Netherlands. Here you can see the figures obtained from Buick et al. 2016 and Buick et al. 2018. And we can observe the location of Hellegat here. We have this is the estuary, Western Scheldt Estuary, and this is the North Sea. And here we have Bath. So we did the validation, as I said, in both places. For Bath, the dominant saltmarsh was Cirrus maritimus. It's important to highlight that this vegetation was not tested in laboratory by Massa et al. So here we could prove if the formulation can be extrapolated to other species. The wave height measurements of the field campaign was carried out that we used was in winter, December. I remember, yeah, December 2014, and the plant height reported by Buick et al. was 70 centimeters approximately, and the biomass we get it from the steam density variation reported by Buick, and also with the Heoner et al. Study. You can see that there's a biomass variation along the transect. We implement, so the model has an input, this layer of, we can call it layer of biomass. at the beginning, so at the end is different. And here we have the validation. As you can see, the model did an excellent performance. To be honest, it was better than we expected here in this case, in these two cases. Well, in black points, we have the wave height measurements in field, and the continuous line is the Swanbeck outcomes. And this is just was with the biomass and the plant height, as I said before, without any calibration parameter. Also, we did it in Heligat. The vegetation that is dominant there, it was Spartina anglica. It was not tested in lab by Massa et al. The wave height measurements were in summer, so we have a different season from bath. The plant height is approximately 50 centimeters, and the biomass we got it from a school et al. Study. Also, we implemented the variation of biomass through the vegetation. We give it two values, the first 15 meters, and then the rest to the second value of biomass. Here we have the validation again for two cases. You can see it wasn't as bad, but at the end, we see a satisfactory result of applying the new implementation in field conditions and with other species like Spartina anglica. So with this, we consider the model can be used for at least 6 species. As you can see, 2 of them were extrapolated. It means that they were not from the laboratory test done by Massa et al. So here we are. I just show you a new way to quantify in a predictive way the Coastal Protection Service with the need of only biomass and plant height. As you can see, both of them are predictive approaches, and both of them help to quantify the Coastal Protection Service provided by vegetation. So we also wanted to compare both methods for the case testing laboratory. And as you can see, the performance of the empirical formulations was not the best compared with the new implementation. But we have to be careful. This doesn't mean that they are wrong. If we see these results at the end, we are applying these equations to vegetation from which they were not derived. So we have to be careful in applying the empirical formula only for the range of application and species for which they were derived, or if not, we could be misleading in the estimation of Coastal Protection Service. So as a conclusion, we quantify the wave attenuation induced by salt marshes with different geometrical and biomechanical properties with a new numerical tool. This implementation is based on a predictive approach. There's no need of calibration. The inputs are biomass and plant height. Also, the model was extended for including biomass spatial variation. At the end, 6 species were validated for in laboratory and 2 in field. So this is the presentation that I have for you. Just in case if you want to contact me, this is my email. You can email me. Thank you very much for your attention. And the next speaker is Juan David Osorio Cano from the Universidad Nacional de Colombia, Sede Caribe, and he is going to talk about the quantification and modeling of hydrodynamic processes around coral reefs. Thank you very much.
Could you please, Valeria, confirm if my...
we are just looking at you. Yeah, we can hear you well.
Okay.
Yeah, we can see the presentation.
Okay, so again, thank you. And thank you, Valeria and Professor Rodolfo, for this invitation. It's a pleasure to be here to see some colleagues and to talk in a friendly way about what we are doing in this amazing topic related with natural-based solutions in coastal systems. What I would like to present now is some of the results that I got during my PhD. It's related with hydrodynamic processes around coral reefs. I'm from National University of Colombia at San Andres Island in the Colombian Caribbean Sea. So as an introduction, I would like first to, just one second. This will be the contents of my presentation. Here I will start with the motivation, then I will go through the hydrodynamic processes around coral reefs, where I will talk from different points of view. One of them will be from the reef scale perspective, and the other one will be from the coral colony scale. And finally, some concluding remarks and outlook. So let's start. Why I'm studying corals. I always like to start with this slide because it helps us to understand why and how important is to preserve one of these or all of these coastal ecosystems. In the case of coral reefs, when we have loss of coral reef habitat, we have a decrease in the way that it can help us to protect from storms or extreme events. And if we have problem with corals here, then we will affect all the other ecosystems like seagrass or mangroves, decreasing also the capacity that they can offer to us. And if we have problems with mangroves and seagrass, for sure we will have problems with land, habitat destructions and changes in nutrients, sediments, and freshwater outputs, with finally loss of coral reef habitat because we will have an increase in sedimentations and nutrient input. So finally, in places like in Colombia, for example, where people depend on tourism and our beaches and ecosystems, it for sure will impact the economical aspects and social aspects there. So I will focus on coral reefs just to let you know that I'm not a biologist, I'm an engineer, but from this perspective, I like to collaborate and to talk also with the other colleagues from the other disciplines to understand the role of corals and how can corals protect us. So in Colombia, we have beautiful beaches, but also big problems related with coastal erosion. And this is, for example, in the Caribbean, Capurganá, where we have the coral reef over here, or in San Andres, where we have the reef crest and the coral reef over here, or also on other islands, very flat islands, which are in fact under extreme events, and it can be really damaged under extreme events. So we want to understand how is the role of how can corals and coral reefs can protect us. So just let's start with the physical process around it. So we can have natural or artificial reefs, but in both cases we have a very complex processes, including refraction, shoaling, reflection, and energy dissipation. It can be due to breaking waves or bottom friction. But the reef is not like a flat bottom like this. It's just a paint of how it looks like, but it is really complex. It has different coral species, different species distribution, and for sure, all of these characteristics and topologies of the different corals for sure will affect somehow the incoming flow. So at that time I had a question related with how and if we should consider corals into wave propagation models to account for energy dissipation, particularly from bottom friction. That's why to put it in perspective, what I wanted to do, first of all, I just have this framework to understand where am I and where I'm going. To explain a little bit this, it is composed by like 4 stages. where stage A is to evaluate what we have, what kind of coastal habitat or natural habitats we have. It can be mangrove, coral reef, seagrass, or sandy beaches. And how changes in bottom roughness can, for sure, how can changes in bottom roughness can affect the protected services provided by them. So there are different methodologies, different ways to approach that problem, but at the end, what we want is to have some tools or some inputs to let the coastal managers take decisions. So just during this presentation, I will focus in this red box to talk about bottom roughness and how bottom roughness can help us or not to give us protective services. So let's start with the numerical models that we can use to understand how roughness can help us. And that's why I start with a process-based method like X-pitch model, where you can define, for example, different frictional coefficients along the reef surface to see or to check what happened with the hydrodynamic characteristics, what happened with the wave height and how is the energy dissipation, how is the run-up, for example. So the other good thing from this model is that you can also evaluate how is the evolution of the beach profile depending on the frictional coefficient you have. So, but the big question here is, what is the frictional coefficient? The short wave friction factor in this case, FW, that is included in the wave propagation model. So this is a big question, and what we use is just calibrate and trying to tuning this kind of friction coefficients to get the best performance of the model. But in some cases, the results of these frictional coefficients doesn't make sense. So while we have some information about, okay, if you have a sandy beach or a light coral or dead coral, you can try with some friction coefficient that other authors got from experiment results or field data, but it's a big issue when you are not sure about which frictional coefficient you want to use. In this case, I perform a sensitivity analysis. I run 96 regular wave tests to check, for example, under different sea water level and different frictional coefficients, what is the effect on the wave height and dissipation and run-up. I want to go faster to show you in this slide, in terms of the beach profile evolution, what is the effect of considering different frictional coefficients from 0 to 1 to see how is the beach profile evolution. So when we have zero, no variation in water level, or we have 2 meters variation in let's say a storm surge or extreme event, then we will have an impact on the beach profile evolution. So in this case, you can see different beach profiles, and one of them, this big change is related when we don't have frictional FW frictional coefficient, or less change when we have one. So which one we should use? That's the question, and that's what I want to focus. How to approach that, because somehow decision makers they need to use software or models like INVEST, like the one Nadia mentioned, or they want to use some frictional coefficients, but they are not sure which one they should use. That's why I decided to try to different methodologies with different numerical models. One of them is a CFD model, where you can explore the possibility to define how is the roughness along the reef. So the study site in this case was Tesoro Island in the Colombian Caribbean. We deploy different pressure sensors and ADCPs to measure waves and currents in a long transect across the reef crest. So you can see here the reef profile, and in the red dots you can see the sensors that we deploy there to measure the evolution of the wave height along the reef. So we have here the reef crest, the forereef terrace, and the outer forereef. This is a picture of how it looks like there. So it's very, very complex. We cannot assume that the reef is smooth or it is composed by only one coral species. So it's very, very complex in terms of ecology. So we have the sensor pressures, and based on the field survey, we explore how is the shape of particularly Acropora palmata coral species. Why? Because in Tesoro Island, the forereef terrace was composed by this kind of corals, but now everything is dead there. So I wanted to explore, okay, what happens if I try to restore the corals, and if we have again corals like Acropora palmata in the forereef terrace, like here, what is the impact on the hydrodynamics processes? That's why we, with the pressure sensors and the numerical model, OpenFOAM, we validate the numerical model with the field data to see the energy along the reef, and with that, and assuming that the reef, the forereef crest is composed by these corals, assuming that them are Acropora palmata, this branch coral, which is able to survive in a high energy, wave energy environments, then I wanted to see, okay, if I have it, or if I remove these corals, what is the impact, or what is the effect, if it's the same or not, if I have the coral or not. So with that, we validate the model. So you can also check the results in more detail in this paper. So we can explore other physical processes that are happening and that we wanted to go in deep. So we can see here in the upper panel, we can see the waves along the reef, and here is a zoom of the outer forereef, and we can see like undertown currents, and something is happening. Actually, we need more data to validate what is happening here, and also to explore the possibility to do it in a 3D model, because now you can see here is just 2D, and also you can see the vertical velocities, horizontal velocities, and the interaction between this fluid and the structure. All this is to understand how is nature working, and try to get the best from them and try to improve it if we can, or how can we help the nature to keep doing the job. Some of the results I want to go to focus on this slide to show you in terms of significant wave height. We can see here the difference between the smooth surface, the red, the black line, and the rough surface, the red one. And you can see the difference here. For sure, there is a big difference in terms of wave energy dissipation or significant wave height. It can be one of the results that we got here is under moderate conditions. Let's say moderate conditions when we have waves below 2.5 meters. I'm talking about Colombian Caribbean Sea, but if you go to the North Sea, will be completely different. And we can see here that just the roughness can dissipate. We found that about 5 to 14% of wave energy. However, on the extreme events, the results seems to be like not too much difference. It seems to be like the same, but the conclusion is that under extreme conditions, the wave breaking is the main physical process that is happening there. Some of the related physical processes that we got is that we can see and anticipate wave breaking under different times. We can see the wave here propagating along the reef, but under rough condition, which is this panel, we can see that the wave is already broken or is broken So we have an anticipated wave breaking when we have a raw surface. The other thing is that we have an attachment of the undertow current when we have a raw surface like this, if we compare with the smooth surface like this one. And also the wave breaking location is changing when we change the surface of the reef. So all of this is just like tips to try to connect all these hydrodynamic processes with the possibility to do some reef restoration. If we want to do reef restoration, for sure, we will have impacts on the hydrodynamics, and we have to go deep into the numerical models to see what will be the impacts. To go more, I mean, it was the analysis at the beginning was in a big scale, but then I have to go for the frictional coefficient. Remember the first point, the frictional coefficient. Which one should I use? That's why we decide to study in a small scale, the coral colony scale, in a laboratory experiments, to try to understand how can we got that those coefficients, or those parameters. So that's why in Braunschweig, in Germany, we perform different experiments in a wave and a current flume, where we deploy a coral colony scale, a single coral colony scale, and a group of coral colony scales. We also put a force transducer to measure the forces over the whole structure, and then we can relate the forces with the drag and inertial coefficient. We will see later. So we performed experiments, and then we also validate the numerical model to get or to expand or to extend the capacity of the numerical model for different conditions that were not tested during the experiments. So we got the numerical model, and then we perform different analysis with different wave heights, wave periods, to see how is the streamlines and the forces on the different conditions in these coral colonies. All of this to finally have velocities, forces, and surface elevation, and with that information it's possible to get the drag coefficient and the inertial coefficient based on the drag force and the inertial force based on the total force measured over the whole coral structure. And with that, it was possible to find that under certain conditions, not always the drag coefficient is important, but also the inertial coefficient is important, particularly when we have like this kind of branch corals, and under these hydrodynamic conditions with with small wave heights from 3 centimeters to 7.5, it was scale 1.18 scale. So we got these functions where we can relate the drag coefficients with the characteristics of the problem. So just to finish, it's because I wanted to let you know that we have to go deeper in this. We have to, as an engineer, and if we want to explore numerical models and we want to give some tools to decision makers, we have to explore and we have to go deeper in this. We still need too much to investigate. We need to go further to see under different conditions what happened with the characteristics of the coral. Now I was thinking with the Fernando presentation, how can I like get this methodology, like for example, studying from the biomass, the characteristics of the coral, and try to do it in a more simple way to get the dissipation from corals based on the biomass, for example. So we still need some research on this. Just some concluding remarks is that we for sure need process-based models to be implemented together with the ecosystem management tools like INVEST, for example. From CFD model, we found that the energy attenuation from the corals are around 95%, where just the reef roughness is about around 4 to 14%. The most relevant element during extreme events is the breaking waves, but under moderate conditions, for sure, the reef surface will have a very impact on the energy dissipation. And conclusion is not a conclusion; it's something that for sure will need is the interaction with the physical and the biological and the biogeochemical disciplines to interact with them. For example, I don't know the impacts of this research in terms of nutrient sediment transport, and what happened if I consider a 3D model, what happened with the long-shore currents and long-shore sediment transport and nutrients. For sure, it will be affected. What is going now? We want to explore in San Andres Island what is the contribution of the reef, coral reef, to this to energy dissipation, particularly due to very extreme events. Last year in November we have Iota, the hurricane, which impact Providencia and San Andres, and we want to explore how was the contribution of that. For that we need field measurements, and we'll need to go further with the numerical model. This is all I wanted to share, and thank you very much for your attention, and I guess we will have time for a couple of questions. So again, thank you very much.
Well, we have some questions that have been made in the chat of Facebook and YouTube. We have here one for Saber. They are asking if varying both permeability and porosity may have also effects in the runoff maxima, and if you have incorporated the assessment of the runoff and flooding into your analysis.
Yeah, so this is actually a very important question, because the idea is that permeability will reduce the erosion volumes, and a reduction of the erosion volumes means that the crest of the dune, or the volume of the dune, which will erode will be much less with lower permeability. This means that this will lead to reduction of the runoff rates, and overtopping rates. And this is actually the idea, that we would like to reduce the overtopping rates and the overflow volume of water. So at the end of the day, reduction of the erosion means reduction of the runoff rates.
Okay, well, thank you, Saber, for your response. We have here another one for Carmelo. Gaby Mendoza asks if, she asks how to deal with in the waveflume experiment with the different scale between real life size plants and the other physical variables of the experiment.
Okay. Well, it was a very big problem, and it is a big problem in waveflume experiments. To deal with this, we generated a one scale dune to avoid the problems with the scaling vegetation, and we deal with the storm conditions. We create like the vision dune profile in order that the bathymetry imitate like or mitigate the waves that were reaching the dune, to only simulate the swash, that is the wave runoff. So we did not have like the real waves, but we simulate the swash. That's the way how we deal with that problem. But there is another solution. Some people simulate all the profiling in another scale, but there is the big problem that plants seems like big trees in that profiles. Okay, we only simulate a swash with the bathymetry.
Okay, thank you, Carmelo. I wanted to share this one with Saber. Somebody asked, what is the main difference between hiding and exposure modification factors for critical shields parameter in comparison with the permeability included in empirical formulas? So
actually, thank you very much for this question. Maria was asking if we mix bentonite with sand. this actually will make the sand a cohesive material. Actually, we investigated this in our geotechnical lab in the Technical University of Braunschweig, and we found not. We are speaking about very small fractions of bentonite, so in the range of 1 to 10% bentonite. So still the sand, we already performed some permeability tests and also some consolidation tests and direct shear tests in order to investigate what is the effect of adding bentonite to the sand. We found from this figure here that the permeability is decreasing with increasing the fraction of bentonite. However, the porosity is not changing, and also the friction, the angle of internal friction, and the cohesion is not changing. So this means that sand, when we add bentonite to sand, it is still behaving as sand, not as a cohesive soil, not as clay. And this means that sediment transport formula for non-cohesive material is still applicable, but there is no limitation because we find that the other soil properties are not changing with adding bentonite. So this was the first part of the question, and the second part of the question was related to what is the difference between adding artificial limiter or accounting for permeability, and this is actually comes here. So adding artificial limiter means that there are many physical processes that are not understood. We are not accounting for some physical processes, and this is the reason why we want to go inside this black box, how the soil is behaving. So we cannot consider the artificial limiters if we can increase our knowledge, and this is what we try to do. We try to understand how the soil is behaving during high flow velocity regimes, and we found that okay, this is actually improves the results of the erosion rather than using the artificial limiter. Using the artificial limiter, sometimes we already proved in a study which is currently under review by the Geomorphology journal that using this artificial limiter sometimes does not provide good results, sometimes making the prediction worse. And this is the reason why we try to account for the dilatancy effect based on Van Ray and more and others effects of permeability. So if we add bentonite, this means that we are decreasing the permeability, but other soil properties remain the same. This decreased permeability, sand will remain sand for tourists. So they will not feel that there are some bentonites within the sand because it's a very small fractions. But this kind of small fractions will expand when we have a storm. Will expand in order to fill the gaps between the soil particles and then reduce the permeability significantly. And this is the idea of this environmentally friendly solution to reduce coastal erosion. I hope this answers the question of Maria.
Thank you, Saber. Many thanks for your response. We have also here a couple of questions for Nadia. They ask, the mangrove fragmentation was analyzed in this project?
Let me see. Could you hear me?
Yeah, we can.
Yes. Okay. In this study, we didn't analyze fragmentation of mangroves. We also only focus on the analysis, the quantification, evaluation of the consistent services. So we look for other kinds of data, but without considering fragmentation. But I think it could be a very interesting issue to analyze for a future study.
Okay, thank you. And we have another one for you. They ask, well, somebody shared with us that tried to use multispectral analysis to evaluate coastal changes and the use of the I can't pronounce the index, but which is the threshold after that is possible to consider the raster pixel as water?
Well, in this study for the mangroves analysis, we used another methodology. We did other kinds of RGB compositions by using another index, that is the NDVI, that is the normalized difference vegetation index. So we didn't work so much with the water class, but I know that some thresholds for values for water, I think that it must be the lowest values for water, but I'm not really sure. Actually, we did this analysis, these RGB compositions and hybrid images, this fusion from with multispectral and radar images with other experts in geospatial analysis. So maybe I can look after this answer with them. So.
Okay, thank you, Nadia. We have here a question for Fernando. They ask if is your version of SWAN vegetation publicly available?
Sorry, do you hear me now? Okay.
Yeah.
No, in this moment, no. We are working in just final details and writing the paper for publishing. So in this moment, there is no a public version. We are working on that.
Okay, thank you. We have here another one for Carmelo. Do you think that this type of vegetation offers a good protection service against events in an extreme regime or only for events with a normal regime?
Well, it is not very clear at all. We suppose that plants can continue offering this service during the wave approach when the storm is initiated. However, if the extreme conditions remove the plants, we can lose this process. And we have to be conscious that, for example, the sediment that the storm demands on the surface zone to form the sandbars have to be repositioned to reach the equilibrium profile and dissipate the waves.
Okay, thank you. Let me see if we have another one in the chat. Well, we have here one for Juan David. Do you know if the health of the corals affects the dissipation that they provide of the wave energy?
Hola, hola.
Yeah, we can hear you.
Yeah, I think yes. We are still working on that because the coral can be alive, but the tissue. I mean, when the coral is white, when we have bleaching coral, the coral is still alive and the structure is still there. So there is a physical structure made by carbonate that is still in the floor, in the surface, in the reef surface, that is still protecting us. But this in a small scale, I don't know how important is the tissue of the coral. If the coral is sick, let's say, maybe there are some interaction, that some hydrodynamic processes happen in there that affect the physical conditions. But in a big way, I think the coral is still protecting us, but certainly somehow at the end, if the coral die, the coral will be degraded. Finally, we will have a decrease in the coral protection. Decrease in coral protection.
Okay, well, many thanks for your response. I guess that's all for the questions. And here we have Andreas Hastrick, that he's the president of the Exceed Syndrome Network. So I will ask him to give us concluding remarks of these 2 sessions of the webinar. And so if you can turn on your camera, thanks.
Yes, Thank you very much, Valeria, for giving me the opportunity to address some closing words with respect to this webinar, and giving us very interesting and informative insight into the research world of coastal protection and coastal engineering. I'm not coastal engineer, but I was really interested, and we had very, very good presentations in my opinion. I would like also, on behalf of the entire Exceed Swindon network, worldwide network, I would like to thank the organizing team of this webinar, especially Professor Rodolfo and his wonderful team. And thank you very much for the organization. And well, I'm a bit reassured after all the presentations that we may still able to avert the worst. I mean, no one can meanwhile disagree anymore with the fact that the climate change and that climate change will have a massive impact on water security and coastal security. So if we keep in mind that in the next 50 to 60 years, most of the world population, almost 75%, will live in coastal areas and in big cities. So then we can imagine what it means, what security means and what coastal protection means. So thank you very much again for giving us this wonderful insight into your work, and thank you very much. And again, thank you very much to all of the presenters and to the organizers. Thank you.
Thank you, Andreas, for your words. Here we have also already Elvis. He is the Latin American representative of this Exceed Swindon network. So Elvis, I don't know if you can turn on your camera and if he can have the permission to turn on his microphone, please. Well, while Luis, can Elvis have the permission to turn?
Oh, can you hear me?
Yeah, we can hear you now.
I'm sorry, I don't know what's going on with my computer now, and I cannot open my can here. But I'd like you to on behalf of the Exceed Swindon network, also to say how proud we are of this memorable webinar organized and conducted by Dr. Rodolfo Casarini and his team at the Universidade Autónoma de México, and Andrés Osorio from Universidade Nacional de Colombia, that reached so many people and so many students and the researchers around this world that are facing or studying similar situations regarding coastal existence. So I'd like to congratulate you all for this important webinar and for this young group of researchers that shared their knowledge with us during these 2 days. So thank you so much.
Thank you, Elvis. So, well, we want also to apologize again because of all the troubles we had with the connections. The videos will be available on the YouTube channel of the Instituto de Ingeniería. You can already see the video from yesterday, and they will edit today's presentations to be available there. So we hope you can watch them later. And well, that's it for us. Many thanks for all the presenters from yesterday and today and all the assistants. So thank you.
Okay. Thank you.